After reviewing various resources on the mathematics of neural networks, I have encountered inconsistencies that have left me confused. In this video, we will explore the multivariable calculus involved in the backpropagation algorithm of recurrent neural networks, RNNs. We will create an RNN from scratch in Python without relying on any neural network libraries. By the end, we will have a solid understanding of RNN architectures and the fundamental math behind them, enabling us to competently train models using various frameworks. Let's consider a formal neuron with a feedback loop. The neuron operates in discrete time steps. For simplicity, we assume all the connections have a weight of 1. If we are given a sequence of values for the input x, we can calculate the output y. If the initial state of the neuron is known, which is normally assigned a random value or 0, a simple recurrent network is built by connecting the output of a layer of neurons back to these neurons. Depending on the task requirements, one or more layers are added on top of the recurrent layer. Let's delve into how a basic RNN operates with time series data. Time series data comprises a series of observations recorded over time, with each data point associated with a specific timestamp. It is utilized for trend analysis, future outcome prediction, and temporal pattern recognition. Time series data exhibits temporal ordering, autocorrelation, and seasonality. For demonstration purposes, let's assume these are weather samples, including data on temperatures, humidities, winds, and pressures. Our goal is to train our network to predict the temperature based on the data from the previous 4 samples, or to predict other variables. The data series can be anything else, such as house prices or blood glucose fluctuations. We will use a many-to-one model to demonstrate how a simple RNN works. The many-to-one model processes sequential data to generate non-sequential output, such as class labels for tasks like sentiment analysis. This is how we build our data set from the original time series data. The model needs an initial value to produce the first hidden state, h. Then, the model sequentially takes the input at each step and calculates the hidden states and outputs. For many-to-one prediction, the output of the last step is compared with the target data for computing the loss value. Before we dive into the Python code, let's see how the hidden states are stored. Commonly, the hidden states are stored in a Python dictionary or NumPy array. The initial state can be positioned either at the end or the start of the array. This code snippet uses the second strategy. The code is very simple. Pause the video if necessary. In this video, we will use lowercase bold letters for vectors and uppercase bold letters for matrices. Scalars are represented by italic letters. We will encounter this rule repeatedly. When we have 2 layouts for the same derivative, we will indicate the layout as either J for Jacobian or G for gradient. The gradient layout is a flipped version of the Jacobian layout. The Jacobian layout is also known as the numerator layout, while the gradient layout is also known as the denominator layout or the Hessian formulation. In discussing RNNs, It is important to know the derivatives of two functions, tan h and softmax. Refer to the link for the derivation of the derivative of the softmax function. Two common loss functions are used in machine learning, the sum of squared errors for regression tasks and cross-entropy loss for classification tasks. The chain rule has different forms for the Jacobian layout and the gradient layout. This can be easily understood by considering the rule that the transpose of a product is the product of the transposes in reverse order. In our previous videos, we showed how to derive formulas for the derivatives of vectors with respect to vectors or matrices, especially when matrix multiplication is involved. These formulas can be verified by breaking them down into components and organizing them in the Jacobian or gradient layout. Now that we have formulas 1 through 12 at our disposal, we can apply them to concrete examples where the loss functions are known. It is important to exercise caution when using these formulas. For example, if vector y is not the result of matrix W multiplied by vector x, formulas 11 and 12 cannot be applied. Let's calculate the derivative of the loss with respect to matrix W. You can pause the video to verify our derivation. Similarly, we can derive formula 18. What is the derivative of the loss with respect to matrix W after adding another layer? Similar to the previous example, we can find the answer using the previous formulations. Let's explore the mathematics of a simple RNN. First, we will calculate the derivative of the loss function L with respect to the matrix V. In a many-to-one network, we only need the output of the last step to calculate the derivatives of the loss function with respect to V. For simplicity, we will ignore the subscript. Referring to formula 16, we can determine the solution. Deriving the loss gradient with respect to matrices U and W can be challenging. Some blogs simplify vectors and matrices as scalars, leading to incorrect intermediate formulations, even though they eventually arrive at the correct conclusions. It is easy to identify dimension mismatches when treating matrices and vectors as scalars. Redefine D4, we have using formulas 1 through 12 to calculate the derivatives of L with respect to U and W is straightforward. The diagram illustrates that you can influence L through 4 pathways. The current explanation provides a detailed description of the operations carried out on matrices and vectors. Treating matrices and vectors as scalars would result in a loss of crucial information. This Python code demonstrates how math is applied to backpropagation in a simple RNN. The code is for demonstration purposes only and is not optimized for the current task. This function converts the time series data into a training dataset. Let's focus on the backward pass. Pause the video to see how the toy dataset is constructed.